Continuation of the previous video, application of remote sensing and GIS in land cover, land use planning and management. So application of remote sensing and GIS in land cover, land use planning and management. Land cover and land use planning and management are critical components of sustainable urban and rural development, environmental conservation and resource management. Remote sensing and GIS technologies play pivotal roles in these areas, offering invaluable tools for data acquisition, analysis, decision making and monitoring. So land cover classification, remote sensing and GIS are used to classify and map different land cover types, which include forests, agriculture, urban areas, wetlands, water bodies and more. These classifications help in assessing the current state of the landscape. Remote sensing, multispectral and hyperspectral imagery provide data for land cover classification based on spectral signatures. So algorithms like supervised and unsupervised classification are employed to differentiate land cover classes. So GIS software is used for image interpretation, feature extraction, and the creation of land cover maps by combining spatial and attribute data. Then change detection, monitoring changes in land cover and land use over time is crucial for understanding trends, assessing environmental impacts, and planning interventions. So remote sensing and GIS facilitate change detection studies. Then remote sensing, multi-temporal satellite or aerial imagery is compared to direct detect changes in land cover such as deforestation, urban expansion, or crop rotation. And GIS tools help in analyzing changes by overlapping historical and current land cover maps, calculating change statistics, and identify areas of concern. So, urban planning, remote sensing, and GIS contribute significantly to urban planning by providing spatial data and analysis capabilities for sustainable city development. In site selection, GIS helps identify suitable locations for infrastructure development such as roads, schools, and hospitals, considering land cover, accessibility, and population density. So, zoning and land use planning. GIS assists in zoning decisions and land use planning by considering factors like land suitability, environmental constraints, and socio-economic data. Then, transportation planning. GIS based traffic modeling and route optimization improve transportation planning, reducing congestion and pollution. Then agricultural management, agricultural planning and management rely heavily on remote sensing and GIS for crop monitoring, precision agriculture and yield prediction. Then crop health assessment. Remote sensing provides data on crop health, identifying stress factors like pests, diseases or nutrient deficiencies through spectral analysis. So precision agriculture. GIS enables precise management of agriculture inputs like fertilizers and pesticides based on spatial variability in soil properties and crop conditions. Then yield prediction. By analyzing historical data, GIS models can predict crop yields, helping farmers make informed decisions. Then environmental conservation efforts benefit from remote sensing and GIS through habitat mapping, ecological modeling, and natural resource management. And habitat mapping, remote sensing helps map and monitor habitats of endangered species, aiding in conservation planning. Then ecological modeling, GIS is used for spatial modeling of ecological processes such as species distribution to understand and mitigate the impact of land use changes. So natural resource management supports the sustainable management of natural resources like forests, wetlands, and water bodies by tracking changes and assessing the environmental impact. Then disaster management. In disaster prone areas, remote sensing and GIS assist in disaster risk reduction, preparedness and response and recovery. So pre-disaster planning. GIS helps identify vulnerable areas and plan evacuation routes and emergency shelters. So disaster monitoring, remote sensing provides real-time data on disasters like floods, wildlife and earthquakes for immediate response. So post-disaster assessment, GIS aids in damage assessment, helping allocate resources for recovery efforts. Then environmental impact assessment for infrastructure and development projects. Remote sensing and GIS contribute to environmental impact assessments, EIAs, by providing baseline data and spatial analysis tools to evaluate potential environmental consequences. So baseline data, remote sensing imagery provides pre-projected data on land cover, vegetation and hydrology. Spatial analysis helps assess the spatial extent of potential impact, allowing for informed decision making and mitigation measures. So, in conclusion, remote sensing and GIS are invaluable tools in land cover and land use pattern and planning and management. So, data driven decision making, support sustainable development, and enable efficient resource allocation. So, professionals and researchers in various fields must have a solid understanding of these applications. Urban sprawling, vegetation study, forestry, and natural resource. So, application of remote sensing and GIS in urban sprawling, vegetation study, forestry, and natural resource management. Remote sensing and geographic information systems are powerful tools for assessing, monitoring, and managing urban development, vegetation, forestry, and natural resources. These technologies provide critical data and analytical capabilities, enabling informed decision making and sustainable management practices. So, urban sprawling, urban growth monitoring, remote sensing, multi-spectral and high-resolution satellite imagery are used to monitor urban growth by comparing land cover changes over time. This helps identify areas experiencing rapid urban sprawl. I'm not sure about the pronunciation. Then GIS-based land use change analysis provides insights into the expansion of urban areas, supporting urban planning and infrastructure development. And land use planning, remote sensing, satellite imagery aids in land use planning by identifying land suitable for urbanization, considering factors like topography, accessibility, and environmental constraints. Then GIS tools help in zoning decisions, land use allocation, and identifying areas for green spaces and conservation. Then infrastructure development, site selection. GIS assists in identifying suitable locations for infrastructure development such as roads, utilities, and industrial zones. Then considering land cover, accessibility, and population density. Then transportation planning. GIS-based traffic modeling optimizes transportation planning to reduce congestion and pollution in sprawling urban areas. Then vegetation study, vegetation health assessment, remote sensing. Satellite and aerial imagery provide data for assessing vegetation health by analyzing spectral signatures. Stress factors like diseases, pests, and drought can be detected. Then GIS tools help in mapping and spatially analyzing vegetation health, supporting ecological studies and conservation efforts. So biodiversity mapping, remote sensing data is used to map vegetation types and ecosystems, aiding in biodiversity studies. So different vegetation types have unique spectral characteristics. GIS-based habitat modeling and spatial analysis contribute to the conservation of biodiversity-rich areas. Then forest management, forest inventory, remote sensing, satellite and airborne disease sensors provide data for forest inventory, including tree species identification, canopy height, and volume estimation. Then GIS is used for spatially organizing forest inventory data, supporting sustainable forest management and planning. And forest health monitoring, remote sensing helps monitor forest health by detecting signs such as disease outbreaks or insect infections. Then GIS-based spatial analysis assists in identifying areas with declining forest health, facilitating targeted interventions. Then deforestation detection, remote sensing. Satellite imagery is essential for detecting and monitoring deforestation events, enabling timely intervention and conservation efforts. So GIS is used for change detection analysis, calculating deforestation rates and identifying the drivers of deforestation. The natural resource management, water resource management, remote sensing. Remote sensing data aids in monitoring water bodies, estimating water quality, and assessing changes in water availability. Then GIS supports watershed management, flood modeling, and the identification of pollution sources in water bodies. So soil conservation, remote sensing. Remote sensing helps map soil properties, erosion, and soil moisture content, supporting soil conservation efforts. GIS-based erosion modeling helps in identifying vulnerable areas and implementing erosion control measures. GIS-based erosion modeling helps in identifying vulnerable areas and implementing erosion control measures. Then mining and energy resources. Remote sensing, satellite imagery is used for mineral exploration, monitoring mining activities, and assessing the environmental impact of mining operations. Then GIS aids in site selection for renewable energy projects such as solar and wind farms. by considering factors like topography and solar radiation. So, in conclusion, remote sensing and GIS are versatile technologies with diverse applications in urban sprawling, vegetation study, forestry, and natural resource management. They contribute to informed decision making, sustainable development, and the conservation of vital ecosystems. So, professionals and researchers in various fields must have a comprehensive understanding of these applications. And waste management and climate change. Waste management and climate change interactions, impact, and mitigation. Waste management is a critical aspect of modern society encompassing the collection, disposal, and recycling of various types of waste generated by human activities. At the same time, climate change is a global challenge caused primarily by the buildup of greenhouse gases in the atmosphere. These two seemingly distinct areas are intricately linked, and understanding their interactions is essential for addressing environmental sustainability. Sources of greenhouse gas emissions from waste. Waste management activities contribute to GHG emissions, greenhouse gases emissions, through various processes like landfills. Landfilling is a common waste disposal method where organic waste decomposes anaerobically without oxygen, producing methane, a potent GHG. So, methane emissions from landfills can be captured and utilized as an energy resource, mitigating their impact. Then, waste incineration. Incineration of solid waste, can release carbon dioxide, nitrous oxide, and other pollutants into the atmosphere, contributing to GHG emissions. Then, modern incineration technologies employ emission control systems to minimize GHG release. And transportation and collection. The collection and transportation of waste generate GHG emissions mainly from the use of fossil fuel powered vehicles. Then recycling and waste reduction. So, recycling and waste reduction efforts reduce the need for the production of new materials, thus lowering GHG emissions associated with resource extraction and manufacturing. So, impacts of climate change on waste management. Climate change has several direct and indirect impacts on waste management practices. Increased waste generation. Extreme weather events such as hurricanes and floods can lead to increased waste generation from damaged infrastructure and property. So, infrastructure vulnerability. Rising sea levels and more frequent extreme weather events can damage waste management infrastructure like landfills and recycling facilities. Then, shifts in waste composition. Climate change can alter the composition of waste by affecting consumption patterns, leading to changes in the types and quantities of waste generated. Then, mitigation and adaptation strategies. Addressing the dual challenges of waste management and climate change require integrated strategies. Methane capture and utilization. Landfill gas capture systems collect and utilize methane emissions, reducing the release into the atmosphere while producing energy. Waste to energy technologies. Modern waste to energy facilities incinerate waste to generate electricity and heat, reducing landfilling and lowering emissions. GHG emissions, recycling and circular economy. Promoting recycling and the circular economy. Promoting recycling and the circular economy reduces the demand for new raw materials, lowering GHG emissions associated with resource extraction and manufacturing. Sustainable transportation. Transitioning to cleaner and more sustainable transportation options for waste collection reduces emissions from waste management operations. Then, climate resilient infrastructure. Designing waste management infrastructure with climate resilience in mind keeps mitigate the impacts of extreme weather events. Then, education and behavior change. Raising awareness about the environmental impacts of waste generation and encouraging waste reduction and responsible consumption is essential. Then, policy and regulation. Governments play a crucial role in implementing waste management policies and regulations that promote sustainable practices and reduce GHG emissions. Case study. Wasted energy in Sweden. Sweden is a leading example of effective waste management and climate mitigation. The country has nearly eliminated landfilling and incinerates waste to produce heat and electricity. This approach significantly reduces GHG emissions and serves as an alternative energy source. So, in conclusion, waste management and climate change are intertwined challenges that require holistic and sustainable solutions. Mitigating the environmental impacts of waste management while reducing GHG emissions is crucial for achieving global climate goals and ensuring a sustainable future. Thank you for listening.